This lecture is part 1 for Section 3.3 of Math 311, a course on linear algebra at Western Illinois University. This is part 1 of a series of lectures on invertible matrices. So let's first define what invertible matrices are. These are inverses with respect to multiplication. Where this is, and when we talk about the multiplicative inverse of a matrix, we're talking about a matrix where you multiply a matrix times its inverse and you get the identity matrix. So in particular, we're restricting our attention to square matrices, n by n matrices, and we say it's invertible, and A is invertible or I should say, if A is an n by n matrix, an inverse of A is an n by n matrix B, such that A times B and B times A are both equal to the identity matrix. Where again, the identity matrix is the n by n matrix with ones on the diagonals and zeros everywhere else. Okay, so when we don't put anything here, you can just assume that there's zeros. If such a matrix exists, we say A is invertible, and in fact that also implies that B is invertible as well, if you think about it. And this is kind of an analog to this will help us solve matrix equations in some case. For example, if you just take a regular algebra equation over the real numbers like 2x equals 5. How would you do that? Well, you divide both sides by 2, right? And of course, what we were really doing is we were multiplying both sides by the multiplicative inverse of 2, which is of course 1/2, right? And so we would get x equals 5/2, all right? Now, what's motivating us to do here with inverses of matrices is that if we take a system of equations, let's like ax plus b, y equals c, ex plus fy equals g, right? We know that this corresponds to a matrix A, B, E, F times xy equals cg. And if we call this matrix A, and we can call this column vector x, and we can call this maybe v, notice that the similarity between this equation and an equation like this. You would like to, it seems like if we could quote-unquote divide by A or multiply by the inverse of A. And then x would be B divided by A or B times the inverse of A, whatever that is. Okay. And it turns out we can do it this way. We can actually solve systems this way, but we have to find, first of all, we have to find the inverse, and not all matrices have inverses. All right. So we saw lots of examples last time where this might not have a solution, or this might not have a unique solution. And it all depends. However, if this matrix A does have an inverse, then we get a unique solution. Okay, and that's what we're going to be talking about today. Now, the first thing you should note is, well, let's look at an example first. So if A is this matrix 2, 5, 1, 3, and this is, if B is 3, negative 5, 1, negative 1, 2, we can multiply them together. We get 6 minus 5, that's 1. Negative 10 plus 10 is 0. 3 minus 3 is 0. Negative 5 plus 6 is 1. Okay, so we get the identity matrix. This is I2. And then similarly, if we switch the order, we get 6 minus 5, that's 1. 15 minus 15 is 0. Negative 2 plus 2 is 0. And negative 5 plus 6 is 1. So once again, we get the identity matrix. Now, by the way, we know that matrices in general don't commute, but if two matrices are inverses of each other, of course, they have to commute because their product is the identity. Now, important thing to note is not every matrix is invertible. And here are a couple of examples. We have this matrix we've seen before, 1, 0, 0, 0. That does not have a matrix, because if it did, we could multiply it together with its inverse. So if we take this matrix and multiply it by an arbitrary 2 by 2 matrix and set that equal to the identity, well, what happens? This is A plus 0, that's A, then B plus 0 is B, then 0, 0, and then this is going to be 1, 0, 0, 1. Now take a look at this, and it's not hard to see that this can't happen no matter what A and B are, because if these matrices are equal, then this entry has to equal to 0, but this entry, but 0 is not equal to 1. Okay, so it's not possible. And in fact, we'll see that. Any matrix with a row of zeros or column of zeros is not invertible. We'll talk about that later. Now, what happens if we have a matrix where all entries are not 0? Well, if we do the same thing and multiply this matrix 1, 2, 5, 10 times A, B, C, D, and set that equal to the identity, what happens in that case? Well, we get A plus 2C for the first entry, then B plus 2D, 5A plus 10C, and 5B plus 10D. And that's equal to 1, 0, 0, 1. All right, now what's the problem in this case? Well, in this case we have that 2A plus 2C is equal to 1, okay, from this here. So if we multiply this by 5, we should get 5A plus 10C is equal to 5, right? Just by multiplying everything by 5. But from this says that 5A plus 10C equals 0. Okay, so this can't happen either. 0 is not equal to 5. So once again, this is not possible. And you will see that there is a that this row, that the second row is a multiple of the first row. And in fact, whenever you have something happen like that happen, the matrix won't be invertible. And in fact, whenever one row is a linear combination of the other rows, that won't be invertible. And if you remember, what does that mean? If that happens, that means the rows are linearly dependent. Okay, so we'll eventually see that if the rows of a matrix are linearly dependent, then the matrix is not invertible. Okay, but here are just two examples showing why an inverse doesn't necessarily always exist. Okay. All right. So next, we have a few theorems we want to go over. So we've been talking about the inverse of a matrix. We're not really saying, why can we say the inverse? Why is the inverse unique? Okay, well, we're going to talk about that right now. So if A is an invertible matrix, then its inverse is unique, and they'll know it by A inverse. We do not use fractions when we're talking about matrices. Okay, in general, it's kind of bad notation to talk about dividing by a matrix. Instead, we multiply by its inverse if it exists. So why is that? Why does that happen? Well, to show uniqueness, we want to show if there are two inverses, they have to be equal. So if, let's say, AB equals BA equals I, and AC equals CA equals I for some matrices B and C, we need to show that they are equal. B and C are equal. Why do we do that? Well, B can be written as B times I, okay, the identity matrix, and then I can be replaced with with AC if we want, or we can replace it with CA, and I'll just replace it with AC. Okay. And then by the associativity, this is the same thing as BA times C, and BA is equal to I, and IC is going to be C. Okay, so if B and C are inverses, they have to be equal. Okay. All right. Another thing is that if A is an invertible matrix, then a system of linear equations given by AX equals B has the unique solution X equals A inverse of B. And the way we do that is we basically just plug it in. We know that A times A inverse X, again by associativity, this is A inverse of X. And I'm sorry, this should be B here. Okay, so this will be IB, and this is B. Okay, so so A inverse B is a solution, and in fact, basically in this case, if we start from here, and if we already know that an inverse exists, we can just multiply by A inverse on both sides. Okay, and once again, this is I, and so X is going to be A inverse of B. Okay, so here we show that A inverse B is a solution, and then here we show it's the only solution. Okay. All right. Then the next result is probably one of the more interesting ones, is that you might think that, okay, the inverse of A times B is going to be the inverse of A times the inverse of B. But in fact, that's not the case. We have to, order matters when we're talking about matrix multiplication. And it turns out that the inverse of A times B is in fact B inverse A inverse. And we can do that by multiplying AB and B inverse A inverse. If we multiply these together, again by associativity, this is B, or A, B, B inverse, A inverse. And then this of course is I, so this is going to be A inverse, and that's I. And similarly, B inverse A times AB will be B inverse A inverse AB. A inverse times A is I, so this is B inverse B, which is I. All right, so B inverse A inverse does act as an inverse, and because the inverse is unique, it has to be the only inverse. Okay, so I will just say by the uniqueness of inverses. Okay, that is theorem 1, which we just had up here. The inverse of AB is in fact B inverse A inverse. Okay. Okay, so something to keep in mind. All right, now that's all well and good. There are some other properties of inverses that you can read in your textbook. This is probably these are the most important ones. And the question is now, okay, well, inverses are great if we can find them. Okay, the question is, how can we find them? So that's what we want to talk about next. Okay, page 3. So how do we find the inverse of the matrix if it exists? Okay, so what we have, if A is an n by n matrix, we are trying to find another n by n matrix X, such that AX is the identity matrix. All right, now the way we do this is we can think of, write down X in terms of its columns. So we'll let X1 be the first column of X and so on. And then we also know that the identity matrix. We know what the identity matrix looks like. The first column will consist of 1 followed by all zeros. The second column consists of 0, 1, 0, and then all zeros, and so on. So they consist of these column vectors EI, which consists where the EI column vector has a 1 in the ith component and then zeros everywhere else. And therefore now then this equation can be written as A times X. Remember, A times a second matrix, that product can be written as columns, and the columns will be AX1, AX2, and so on. Okay, where the XI's, these XI's these are all indeterminate variables. Okay, remember this is X has basically is an n by n matrix, so it has n squared unknown variables, right? So it can take Xi just to be the column vector X1i through Xni. Okay, and then this becomes AX becomes this, and IN becomes this. And what we says is this column has to equal this column, the second column has to equal the second column here, and so on. So we get AX1 equals E1 and AXN equals EN. And what we have is just basically n equations which are almost identical. They have the same coefficient matrix, right? The variables will be different, and the constant term will be different, but the coefficient matrix will be the same. And this system, so here we have n different represent n different systems of linear equations, and we know from a previous chapter we know how to solve systems using Gaussian elimination. We write the coefficient matrix and we write the constant term for the constant vector, or the constant terms here, and then we use Gaussian elimination. Now, notice that the very same elementary row operations we use here to transform this into reduced row echelon form are going to be the same operations we use to transform this into reduced row echelon form. Because really we just need to reduce the coefficient matrix to reduced row echelon form. And if we can do that, if this is if this is truly invertible, then we're going to get, there's going to be a unique solution for each of these. So that means the reduced row echelon form will have to involve having the identity matrix over here. So in all of these, what we're doing in all these cases is we're transforming these matrices into these matrices using the same elementary row operations. And then A inverse, just turns out to be X, right? X is the Xn. So this is the first column of A inverse. This is the last column of A inverse, and so on. Now, there's no reason why we can't just do all of these all at the same time, because we're just using, as I said, we're just using the same elementary row operations. Okay, so let's look at, so in short, this is the algorithm for finding the inverse. Given an n by n matrix A, you first write down the n by 2n matrix consisting of the first half consists of your given matrix A, and the second half consists of your identity matrix of the same size. Then you use elementary row operations to put this matrix in reduced row echelon form. Okay. And if you do that correctly, and if it has an inverse, then you're going to get the reduced row echelon form will consist of this having an identity matrix in the first half, and then whatever here is in the second half, that is going to be your A inverse. Because basically that's where these columns are coming from. Okay. All right. So let's just do a couple of examples now. Let's go back to the matrix we've started with. We already know what the inverse of this matrix is, but let's do it this way. So let's say we have 2, 5, 1, 3. So we start with 2, 5, 1, 3, and then we put the identity matrix over here. Okay. And we want to put this in reduced row echelon form. So I'm going to first interchange the two rows. Okay. And then I have a 1 up here. That's good. I want to get rid of this 2. So I'm going to say minus 2R1 plus add it to R2. And so it's 1, 3, 0, 1. Negative 2 plus 2 is 0. Negative 6 plus 5 is negative 1. Negative 2 times 0 plus 1 is 1. And negative 2 times plus 0 is negative 2. Okay. And then we just want to make this pivot element, our pivot element, this element to be positive 1. So we multiply this bottom row by negative 1. Okay. And then finally, we want to get rid of this 3, so we'll multiply negative 3R2 and add that to R1. So this is 0 plus 1 is 1. Negative 3 plus 3 is 0. Negative 3 times negative 1 is positive 3. Plus 0 is positive 3. And then we have negative 6 plus 1 is negative 5. So we get, okay. All right. So this is I, and then this is our A inverse, right? If this is A. Okay. So we start with A, I. We get I A inverse, and so A inverse is precisely what it was and this is from example 1. Okay. All right. Now we're going to find out shortly. There's a nice formula you can use for 2 by 2 matrices, but the nice thing about this method is that we can use this for any size matrix. So let's look at another example. Let's look at a 3 by 3 matrix. And let's say we wanted to find the inverse of this. Okay. So now, in this case, we have, we'll set up the same thing. We'll put our original matrix, 1, 0, 2, 1, 1, 3, 0, negative 1, 1. Then we put the identity matrix here, which now is a 3 by 3 identity matrix. Okay. All right, and we proceed to reduce this into reduced row echelon form. Okay, well, we already have a 1 here. That's good. I want to get rid of this 1, so we'll do minus R1, add that to R2. And so we get 1, 0, 2, 1, 0, 0. Negative 1 plus 1 is 0. 0 plus 1 is 1. Negative 2 plus 3 is 1. Negative 1 plus 0 is negative 1. 0 plus 1 is 1. 0 plus 0 is 0. All right, next, okay, so we're done with this column. Fortunately, in the second column, we already have a 1 where we want it, so we just want to get rid of this negative 1. So we'll do minus R2 plus R3. Okay, so this will be negative 0 plus 0 is 0. We just want this to add R2 to R3. So 0 plus 0 is 0. 1 plus negative 1 is 0. 1 plus 1 is 2. Negative 1 plus 0 is negative 1. 1 plus 0 is 1. 0 plus 1 is 1. Okay. And then, okay, we're done with these first two columns. We want to make this entry a 1, so we'll multiply the last row by 1/2. Okay. knew we were going to get fractions at some point, right? And then we want to clear out these two entries, so we'll do minus 2r3 plus r1 and negative r3 plus r2. So that gives us, okay, so that is, this is will be 1, 0, 0. Then negative 2 times negative 1/2 is positive 2. No, I'm sorry, it's positive 1 plus 1 is 2. Negative 2 times 1/2 is negative 1 plus 0 is negative 1. And then this is going to be negative 1 plus 0, that's negative 1, I think. And then we have 0, 1, 0. Then we have 1/2, positive 1/2 minus 1 is negative 1/2. And negative 1/2 plus 1 is positive 1/2. And then negative 1/2 plus 0 is negative 1/2. And then over here we get 0, 0, 0, 1, negative 1/2, 1/2, 1/2. And let me just check and see if this works. I didn't make a mistake here, which I sometimes do. Okay. Yes. Okay. I think this appears to be correct. I did this a couple times. Okay. So A inverse then. Okay, and if we were to multiply these two matrices, you'd find out you get the identity matrix. Okay. Yeah. All right, and when you're doing this in homework, and I ask you for the inverse, and you should give me the inverse by itself. You don't leave it like this that say I'm done. Okay, say what the inverse is. All right, now this is just like solving systems of linear equations by reduced row echelon form. The only way you're going to get good at this is to just practice. Okay, and to be fair, a lot of times the calculations won't be this nice if you call this nice. All right, so you can do this. You definitely want to use this method for a 3x3 matrix or bigger matrices. There is one nice little formula for a 2x2 matrix. And that brings us to our next theorem, theorem 4. It says just only for 2x2 matrices, which is the inverse of A, B, C, D is equal to this expression where we have D minus B minus C, A, all divided by the number AD minus BC, assuming that if it's zero, if it's not 0. If it is 0, this doesn't make any sense, and it turns out that this matrix is not invertible. Okay. So this is actually a special case of Cramer's rule. Okay. And the quantity AD minus BC, we call it, that actually has a special name. That's called the determinant of a 2x2 matrix. We are not going to talk about determinants just yet, but I'm just going to show you where does this come from. Well, remember, in a more general way, we are general problem of solving an equation with two equations and two unknowns, like ax plus by equals, let's say, w1, and cx plus dy equals w2, let's say. And if we just want to do this using basic high school algebra, and let's say we wanted to solve for y first by killing the x terms, we can multiply this top row by c, and we'll get acx plus bcy equals cw1, and we can multiply this row by a, and we'll get acx plus ady equals aw2. and we can subtract the first equation from the second. The x terms will cancel out, and we'll get ADY minus BCY, which is the same thing as when we factor out the y. This is AD minus BCY equals CW minus CW1 plus AW2. And assuming that this difference is not 0, we get y will be minus CW1 plus AW2 over AD minus BC. Okay, so that's a formula for y. And then to get a formula for x, we do the same thing. We just eliminate the y terms, and it looks like the easiest way to do that would just be multiplying this top row by D and the bottom row by A, I think. Is that right? Okay. So this would be actually yeah. Let's multiply it by what? Let's see. No, I'm sorry. We want to multiply this by D. Okay, so it's a ADX plus BDY equals W1 times D, and then we'll multiply this by B. We'll get BCX plus BDY equals B W2. Okay. And we can subtract the bottom equation from the top equation. We'll get AD minus BC times X plus 0 equals W1D minus BW2. Okay, so X will be W1D minus BW2 over AD minus BC. Okay. All right. So actually what we've done here is we actually have a general formula to solve any 2x2 equation, any 2x2 system of equations. Just using basic high school algebra. And to find the inverse, we're trying to, we want to, remember, we want to, in the first column, if we, in the first case, or first column of the inverse, we want W1 to be 1 and W2 to be 0. And if we do that, then our X is going to be 1 times D minus 0 divided by this expression. And then Y is going to be negative C, let's see, it should be, negative C over AD minus BC. And then to get the second column of the inverse, we let W1 equal 0 and W2 equal 1. And then X will become, in this case, W1 is 0, so we get over here 0 minus B, so this will be minus B over AD minus BC, and Y is going to be W2 is 1. We're using this one for the Y, so this will be A over AD minus BC. Okay. So that's why this is the first column, which is what we get up here, and this is the second column. Okay. And again, where exactly is this going on? We were once again we were just trying to essentially solve a whole bunch of two systems of two unknowns at the same time. Okay, now I'm just doing it this way because I guess we could I won't write any more because you're not going to have to do this on a test, right? I just wanted to show you where Cramer's rule comes from. Actually, and the more interesting part is actually these two formulas here. But since finding the inverse essentially corresponds to finding a solution to a system of equations, this is how we do it, and that's where this comes in. So if you want to find the determinant of a 2 by 2 matrix, feel free to use this formula. If it's by any other matrix, like a 3 by 3 or bigger, you have to use the Gaussian elimination formula which we did in the previous example. Okay, so all I can say is you get lots of practice finding inverses, and then appreciate what their use in solving systems. But also you're also going to focus a little more on which matrices are invertible and which are not, because basically all types of square matrices can be put into one or two categories: invertible and non-invertible. And there are a whole bunch of invertible matrices have a whole bunch of traits that you can use to determine if they are invertible or not. Okay, so we'll be talking about that next. So that concludes this part. In the next lecture, we're going to be talking about elementary matrices.